Hello, and welcome to Lecture 23 of AMAT502 at UAlbany. Today, we're going to conclude our series of classification algorithms in the subject of decision trees and entropy. This continues our sort of exploration of probability as it helps influence our way of decision making. So at a high level, the topics for today are going to be decision trees, which should be a familiar concept for most of you. Entropy of a partition, and information gain. This all sets us up for the Id3 algorithm. And we'll have an example with a data set regarding hiring decisions. That'll be a theme in one of our next lectures where we talk about what do you actually need to do to succeed with a data science career. Now, since we've discussed SVM, I want to share with you some exciting developments. So a group of researchers at Colorado State University has recently made precise this observation that I alluded to in our last lecture, where we talked about how many points are needed to define the support vectors when using a linear classifier. So Henry Adams, Brittany Carr, and Ellen Farnell, Henry Adams being one of my colleagues at Colorado State, and Brittany being one of his students, recently proved that under these sort of generic assumptions, you can actually have anywhere between 2 to n+1 support vectors. If you're interested in seeing how the topics we're discussing are still active research problems, I encourage you to take a look at this recent preprint on the archive. It was just posted November 1st, 2020. So again, math is an exciting area where there's still a lot of things to do. Additionally, I want to point out that one of the topics they use, or methods they use in this paper, is something called Redon's theorem. Now, Redon's theorem, along with Helly's theorems and some of these other generalizations, are all part of any good education on convex geometry and linear programming. So I'd encourage you to maybe consider augmenting your education by looking at either Bertsimus and Tsitsiklis's Introduction to Linear Optimization. I've shown here a figure from that, or alternatively, you can use Matusik and Gardner's understanding and using linear programming. Linear programming essentially asks the question of, suppose I have a convex shape, one cut out by hyperplanes, and I pick a direction. How do I find the furthest point in a given direction? Now, generically, this always ends up at a vertex, but the algorithm, which actually helped us navigate to that point, called the simplex method, is listed as one of the top 10 most important algorithms of the 20th century. So if you're really serious about expanding your knowledge, both in linear programming, convex geometry, and computer science, you should consider taking a course in this subject. Additionally, although I'm not certain we'll be able to give it proper justice, I know some of you want to use neural nets in your project. This is a nice little beach read here called Deep Learning by John Kelleher. It's sort of a thin, small book, about the size of my hand. And so this is just a very sort of easy to read with sort of nice typesetting. Anyhow, those are some references, but let's move on with the lecture. All right, so what is a decision tree? So we're going to think of a decision tree in slightly more formal language. You could think of it as a tree which you follow different branches depending on the decision you make. Maybe more precisely, you could think of it as a locally optimal search algorithm that uses a test function to iteratively split your data set. The decision tree can be viewed as a graph in which each internal node represents a test on this attribute. Again, in the sort of setting of sociological data, looking at maybe age and income and things like this, these might be attributes which we split on, above 40, below 40 in age. Each branch then represents the outcome of this test, and each leaf node represents a class label. Again, the key idea here is leaf node, not internal node. So you're going to follow this sequence of paths through your tree, sort of a garden of forking paths in the sense of Borges, until we actually arrive at our class labels. So this is really a classification algorithm, and it's one that's not necessarily driven by geometry, although it could be. The paths from the root to leaf then represent these classification rules. So we're now getting and expanding our set of more sophisticated classification algorithms. All right, so this picture came out a little bit smaller inside the slides, but we have basically a root where you start with all your data, and then you apply these little decision nodes where you test attributes. So you navigate down to these terminal or leaf nodes, and those then represent your class labels. So you want to think of the purpose of a decision tree as a method for cleaning up our data. Normally just handed a bag of samples where each sample, at least in the supervised learning setting, which we're looking at here, has some class label. It seems all jumbled up. But we want to use a given number of assessments to efficiently separate our data into however many groups necessary in order to have this kind of clean separation. If we know what questions to ask in order to separate our data, we have a better chance at making predictions just by using the answers to those questions. And so then this shows us that when we want to go and test our classification rules, see how good they are, we then just use these sort of questions as discovered by this decision tree. So just to be clear, again, decision trees fall into the category of supervised learning algorithms. And that is mostly used in classification tasks. But there are decision tree methods for both categorical and continuous labels. So you can use decision trees for regression as well, where you kind of think of regression as having a continuously varying label, like height or weight or age. All right, so just to be a little bit more cleaner, we need to understand what does it mean for data to be messy? And we're gonna do things like, we need to compare the values of features associated to each data point, and then make a decision or cutoff value, which separates our data into two groups. So this is also where, when we think of navigating down our tree, we're usually going to be interested in sort of binary splits. So let's say maybe an example of a decision rule, we're trying to figure out whether we want to hire or not hire. You can think of that as also as a class label. These are the hireable candidates, these are the not hireable candidates. And so then we're going to split up those groups based on their feature values. But either way, all of this is sort of building up to the natural question of how do we know we've made a good separation of our data? So this is where we get to bring in some more notions from probability, courtesy of a mathematician by the name of Claude Shannon. And this is called entropy. So entropy basically provides us with a precise definition of how messy our data set is, as we're trying to say, split a data set using test attributes, where maybe for the purposes of explanation, we're first just looking at two possible class labels, red and blue points, hireable or not hireable, Democrat or Republican, what have you. At each state, so at each step of our separation, we're going to sort of decide, are we cleaning up our data or are we making it messier? The idea that the cleanest separation is going to eventually have all the class labels in one bunch and then all the other class labels in another bunch. That's going to be the cleanest thing. You want to think of these sort of separating Legos into bins. So to start to build our intuition for what entropy represents, we want to have a measure of what this sort of uncertainty is. So what this uncertainty is supposed to represent is that if I have split my data and I still have some combination of my red and blue labels, I want to know how certain am I that I'll get it right if I just point to a bin and say, like, I think all of these have the red points. So you want to think of high entropy as basically less certain, and low entropy as more certain. So let's return to this example of us having a bag of sort of red points and blue points. And imagine I do some splitting where I've now separated this out. And again, just to count briefly, I've got, all right, 5, 8, 11, 13 points. And then I separate them into a set with 6 points, another set with the remaining 7 points, 4 and 3. So I've partitioned my data with 13 points, which are labeled red and blue, respectively. And I've split them. And now I've got a bag where I've got mostly blue points and 1 red point. And then I've got one that's mostly red, but with 2 blue points. So just based on this idea of like, when do you think you're going to get your answer right most of the time? Which of these boxes have the highest entropy and which have the lowest entropy? Well, if you just stare at this root node where we haven't done any splitting, this is where we're gonna, if we just decide to call the points in that box red, we're gonna be wrong, you know, for 7 out of 13% of the time. And so like that's high uncertainty. And that high uncertainty corresponds to high entropy. So that's why, again, entropy is uncertainty. So high entropy, high uncertainty. Now, if you think about this here, if I just predict all my points to be blue, you know, I'm going to be right 6 out of 7% of the time. So that's higher certainty, low uncertainty, and thus low entropy. So if I had to rank these, this would have the highest entropy, this would have the lowest entropy, and this would have the next lowest entropy. All right, so let's be a little more precise. And I kind of alluded to the calculation already, so let's give you the general formalism. So suppose we have a set of n data points and that these 2 points fall into our 2 categories. Let's say that n have label 1, think of that as the red, and m, which is the complement, capital N minus m, have label 2. Those are our blue points. To get our data a bit more ordered, we want to group them by labels. And so we need to introduce this just notion of ratio of how many have label 1. That's going to be p%, that's n, little n over big N. And then we have q% have our blue labels. That's our little m over big N. So that gives us an idea of just, you know, how much, what's our percentage distribution. You know, an important thing to be aware of in classification problems is that often we do have class imbalance. So even, you know, I think there's like an example in the Wisconsin breast cancer data set where I think a majority end up being something benign tumors and only a minority end up being malignant. Anyhow, we then think of this ratio as basically giving us a Bernoulli random variable, where if we want to like look at a point and then ask, well, suppose I don't know what class it is, like that's been hidden from me, then, you know, I could always, if I've got some sort of training statistics of like what percent belong to each of these classes, I could predict, you know, whichever of these P or Q is higher. But either way, the bottom line is the outcome of once I reveal that point's color is a Bernoulli random variable. You know, it's going to be red with probability P and blue with probability 1 minus P, which we call Q for short. This is all just to set you up for, you know, the general definition of entropy of a random variable, where you have some distribution. Let's say it's a discrete random variable. You've got some distribution on n possibilities. There's a notion where you just basically take that probability and you look at log of that probability. But in the case of a Bernoulli random variable, this definition collapses to something more simple. So we can think of the entropy or uncertainty of our data. Again, this being the sort of our Bernoulli random variable of like, am I labeling this point red or blue? Well, the definition of entropy when we have 2 class labels is then I look at minus P, that's the percent with label 1, times log base 2 of P, minus Q, which again, remember is 1 minus P, and then log base 2 of Q. So first thing we're going to make some observations is this is an entropy function, which we can define, at least in this case, we've only defined it for Bernoulli random variables, where the probability of a success or a red point is P. So you might ask yourself, you know, what is the messiest or the most uncertain random variable if we're taking entropy as a definition of uncertainty? Well, if you think about it, and we'll even just plot this equation is going to be maximized when P equals 0.5. That means when there's a roughly 50-50 split. So let's just go ahead and check that for ourselves. So here what we've done is, I'll just run it again. It's gone ahead and graphed this function, and you can see very clearly that it's got a maximum at x equals 0.5. So just as a reminder, like being able to like take a function like the one we just defined and then quickly use matplotlib to produce a plot of it is, I think, one of the necessary bare bones requirements of getting through this class well. So make sure you know how to do these sort of basic plotting operations. Right. So as I already alluded to earlier, we can think of our classification problem as being like a probability distribution on those n class labels, which here really has the concrete interpretation of, we think of probability as just being the proportion of our data set that has class label 1. So we can kind of learn this probability distribution again when we look at a training set, and we hope that the training set is representative of the whole data set so that our deviation isn't too far when we go to test. Anyhow, if we've got a bag of data which is labeled with n possible labels, or again in the supervised classification branch of machine learning, we can define the entropy of our data as the sum from I equals 1 to n of pi, which is the percentage of the data that has class label I, times log base 2 of pi. And so then written out longhand, that's exactly what that looks like. So one thing to note is, go ahead and plug in some numbers for this, maybe in the case where you have 3 class labels. Like in the iris data set, we had 3 different species, iris, vertosa, virginica, and I forget what the other one was. But anyhow, always play around with what happens if, let's say, it's a probability distribution. It's a finite probability mass function. That means they all have to sum up to 1. So if let's take one of these PIs to be very close to 1 and then the rest close to 0. Well, what does that turn into? Well, you've got 0, let's say 0 times log 0. You have to be a little more careful about what that converges to, but again, you can think of that as basically being 0. And then also when we have 1 times log 1, again, log of 1 is also 0. So this entropy is very small whenever we have, let's say, all the PI close to either 0 or 1, which basically means that all my data falls into basically one class label. Again, that means we can, with good certainty, i.e. low uncertainty, low entropy, predict the class labelable point just by predicting the one that's most prominent. Anyhow, I also leave it to you to just think, why is it that we have this minus sign here? So take a moment to just think about that. All right, so let's go ahead and program this, and we'll just write a new definition, a new function. So let's call this entropy class labels. And I'll bring this into memory. So we have given a list of class probabilities, compute the entropy. So we could think of this as a list. And what's basically going on here is an example of list comprehension. All right, so. And notice we've gone ahead and instead of having to deal with what this limits to when p equals 0, we just use only the p's that are non-zero. Now if p equals 0, then this conditional in our list comprehension tells us to skip it. All right, very good. All right, so let's go ahead and revisit an example that we considered in one of our projects. This was the k-means project where we looked at the entropy, or we looked at grade distributions. One decided by a professor at Duke, and the other decided by our algorithm, k-means. So in various iterations of this class, we call this project 3, but I just call it project k-means. So anyhow, we're gonna automatically grade students using k-means, and we set I encourage people to use the random state equals 0. We got this distribution of grades. Grades, again, we want to think of as class labels. 24 A's, 29 B's, 23 C's, 13 D's, 6 F's. And then by contrast, our Duke professor gave 45 A's, 33 B's, 11 C's, 5 D's, and only 1 F. So you can definitely see how it's skewed towards A's and B's. So just to see how this code works, let's imagine, I supply this list, and I can just think of this as a list of who got what. So how many people in my data set had a given class label. Now, of course, this ended up adding up to 95 students, so then we can turn this into a distribution, again, just by using list comprehension. And so let's go ahead and run this code cell and see what happens. So notice that the entropy provided by k-means was much higher than the entropy provided by the Duke professor. Because again, if you think most carefully about that general definition of entropy, it's something that's kind of maximized by the uniform distribution. And so the k-means algorithm was sort of tending towards like a uniform distribution of grades, whereas the Duke professor tended to, slant towards A's and B's, which meant that if you just had to guess what grade a person got when they went to Duke, you'd be pretty safe in betting that they got either an A or B. And again, that actually accounts for, 78 out of 95 of the grades for A's or B's. So it'd actually be very surprised to learn if someone got not an A or B. Anyhow, we're going to put these concepts together to get to our whole iterative split method. And so we want to think of this splitting as basically a partition task. Again, we thought of partitioning normally in the set of clustering, but we can also think of that in terms of navigating towards a good classification algorithm. Our goal is to partition our data set in such a way that we eventually arrive at the intended grades or intended class labels. All right, so right now we have the notion of the entropy of a data set, which is just a bag of samples with labels. And now we want to talk about what's the entropy of a partition of that data set. And so just as sort of a guiding principle, we want to have a partition to have low entropy if it splits the data into subsets that themselves have low entropy. So again, we kind of think of this as we shuffle around the points and then we reapply the definition of entropy of a distribution within each partition. This should remind you a little bit of how we defined overall purity in terms of the weighted average of cluster purities. All right, so what this is going to eventually lead us to is this notion of information gain. So when we partition, how much information have we gained? So let's think about that. So we've got our data set S, and we're going to imagine partitioning this into M partitions, even though, let's say, there are N class labels. And so we're going to define the entropy of a partition just like we did with overall purity. It's going to be a weighted average of the individual entropies of each partition. So that's, again, what you think of this as an expected entropy across this partition. And so again, expectation is the same thing as average. Anyhow, notice that the number M of sets in the partition is not necessarily equal to the number N of class labels. So this means that there'll be sort of inherently some mixing, at least in the case where, let's say, M is less than N. And that's essentially a pigeonhole principle argument. Anyhow, we can think of the information gained as then you took at the entropy of your data set where you've made no partition, essentially have no clustering or classification rules. But now you look at it, imagine I partitioned it into my M sets. And you can compare how has the entropy changed. And I think with some thought, you can always convince yourself that this number should be positive, so that the entropy of each of the partitions necessarily has to be less, and then maybe average out to be less than the entropy here. So if you just want to make sure you're understanding this correctly, think about if you're allowed to choose m to equal n, what would be the partition that maximizes information gain? Well, it's the one that puts all the points of a given class label into its own partition. Because then when you look at the entropy of each of those individual partitions or sets in the partition, we're in that setting where nearly all our points are of a given type or class label, which we already convinced ourselves meant to have low entropy. So let's again revisit our k-means project. So k-means A had 24 Duke A's. The k-means B cluster had 21 Duke A's and 8 Duke B's. The k-means C cluster actually consisted entirely of Duke B's. That's because just there were so many B's. And the k-means D cluster had a few B's and then all of the Duke C's. And then the k-means F cluster had all of the Duke D's and the one Duke F. So basically, k-means failed all the students that Duke gave a sort of honorary D. So let's analyze the entropy of this partition. So we're now again in a setting where we've got 5 class labels, and even though we've got 5 partitions, the k-means partition was not necessarily equal to the Duke partition. And so now we can actually look at what was the information gain in this process. So here I've listed again just the distributions viewed as sort of probabilities across each of these. So remember, all of these were A's. Then we had a bunch of B's and then a few C's. Sorry, let's make sure I have that right. Oh yeah, there were more Duke A's, but again, there ended up only being 29 points in that. So something 21 out of the 29 points in the B cluster ended up having this class label of a Duke A, and 8 had the class label of Duke B. Notice here we're not again trying to match like, oh, what was the sort of difference in these sort of classification algorithms. We're just looking purely at entropy. So again, if I run this, you can see that the entropy of the k-means partition was 0.38. So again, that just got us at the overall entropy of that partition. And so when we went from the unordered down to the if we went from the unordered, unpartitioned data set, where we just looked at the distribution of labels as gotten by all of, so that was k-distro. So again, k-distro, let's just remind ourselves. Right, so this was the distribution of grades as given by k-means. Also, and then d-distro was looking at the distribution as given by Duke grades. Anyhow, just out of curiosity, what's the difference between this and? So there's more information gain, just because the entropy already of the Duke distribution was lower. So then this partition entropy ends up being, doesn't depend on the what was the overall partition. All right, so, and then notice we can kind of compare this with overall purity. So I ask you to maybe think a little bit about how these notions of information gain and purity are related. If you have any good insights, please see me. All right, so I want to take a quick step back to consider some of the context for some of these ideas, because I've just sort of thrown a lot at you. Again, the notion of entropy I just defined, if you've taken a basic probability course, you can understand the definition, but you maybe not understand where it comes from. And again, we've used this term of information gain, but what is information really? And so let's take a quick step back in time to someone who really helped change the landscape for the 21st century back in the 20th century. And this is a person by the name of Claude Shannon. And so, obviously in the discrete case, we could think of this sum of probabilities times the log probability as entropy. And in a continuous distribution, we could also look at the integral of this expression. And anyhow, apparently Claude Shannon, spent some time and talked to John von Neumann, who's another really eminent mathematician of the 20th century. And Neumann basically said, you should use the word entropy or define your quantity of entropy because nobody really knows what entropy actually is. Anyhow, Shannon's a really interesting character. He went to college when he was 16. When he was at MIT doing his master's thesis, he finished at 21, which he basically defined digital circuit theory using this whole notion of sort of logic circuits. So he essentially created a formalized notion of logic circuits using, by the time he was 21. And then this eventually rolled out 3 years later to his PhD thesis when he was 24. Back then, of course, many of you probably don't remember, but Ma Bell was essentially a monopoly. But one of the things the monopoly afforded them is to have a really productive research lab that could be very theoretically driven. And so Shannon worked at Bell Labs, and this is back when some of the best research in the country was happening in Bell Labs. And he then defined this notion of an information theoretic entropy, and in fact coined the word bit. So as you know, everything our computer is built on is this sort of notions of bits and bytes, which basically just thinks of information as being a 0 or 1. And he did this all by the time he was 32. Bishop's book on pattern recognition and machine learning, again, a great Bayesian text, which I encourage you to consider picking up. Bishop gives a really nice explanation of why you should think of this expression for entropy as somehow related to information. And so the way you want to think of this is information is the degree of surprise of learning the value of a random variable x. So if you observe sort of two independent events, let's say the event where big X, a random variable, is equal to some specific outcome, little x, and maybe you have this, again, this independent, you also learn that an event where x equals y, then sort of axiomatically you would think of, all right, well, these are independent things, so I should think of the information gained from each of these observations as being independent, as being separate. And so, just out of algebraic convenience, we might say, I'm just going to sum the amount of information I gained from those observations. So this says that, if H is defined on a pair, then I should think of that as being equal to something like H of X plus H of Y. Now, recall that in independence, the probability of an and, x equals x and x equals y, should turn into the product of those probabilities. So then the question is, how do you go from a product to a sum? Well, we sort of have a universal operation for doing that. It's the logarithm. And so this was essentially what leveraged this first observation that information should turn products of events into sums. And so we can think of h of x as being related to the probability mass function via sort of a logarithm. And if you haven't figured out yet, the reason we put this minus sign is because we want this to be positive. We want to think of information gained, not information lost. It feels like forgetting, and we don't want to model that yet. Anyhow, then we need to sort of make this well defined to say like the probability of an event gets closer and closer to 0. And so of course, if you think about the graph, the log function, it shoots off to minus infinity as you approach 0. And so you want to somehow get rid of that bad behavior. And so maybe an ad hoc hacky solution is just to say like, well, let me regularize this by multiplying by p of x, so that I know that the limit of this expression is well defined. And that's maybe an unsatisfying, but at least sort of mathematically driven in sort of principled, at least, approach to why information or entropy is defined the way it is. It's probabilities times logs of those probabilities, and then summed up with a negative sign in front. So anyhow, we've been using the letter E to refer to our entropy, but because E for entropy, but different texts use different notation, and one thing you should be aware of is this notation H for entropy. And so this all just allows us to recap this definition of entropy that I already gave. Anyhow, let's go ahead and consider another data example. Sorry, I just want to make sure that didn't miss anything though. All right, so imagine you're in the process of, you're in your new startup, your company's growing, and you need to hire more people, more coders. So how would you come up with maybe a decision rule for deciding whether or not to hire someone? And maybe we want to do this, automate the process a bit by basically looking at some attributes of potential candidates. So let's go ahead and look at this. So again, we have these pairs, input and then label, where each input is going to be a dictionary of candidate attributes. You want to think of those as sort of the features. Attributes or features or synonyms. And so this label, we're going to go ahead and use true. Candidate's going to interview well, means we're likely to give them a job offer, or false. Candidate interviewed poorly, we're probably not likely to give them a job offer. And so let's look at what these attributes are. So we might look at the candidate's level. Are they hiring for maybe a junior, medium, or sort of senior position? Their language, preferred language, coding. So, is it Python or R or C or what have you? And then maybe you're asking the question whether or not this person is active on Twitter. And then finally, since there are some of you that are in the PhD program, the question of whether or not this candidate has a PhD. So let's go ahead and look at that. So just to be clear, we're going to use some of these functions here. So we're going to import collections as C. This came from an earlier definition. Either way, total count is going to be the length of our labels. And then we're going to just return this, again, list comprehension, where we look at count divided by total count for count and c.count our labels. And so we also are going to look at some of the labels here, where we sort of iterate through our labeled data. All right, so let's go ahead and bring that into memory just to make sure we've got this. I notice we've already defined these sort of entropy functions. And so we just need to think of this as being some already existing package for inside of I should say class inside of Python. All right, so let's just go ahead and bring that in. Again, I'll leave it to you to sort of read through these things in a little more detail. But let's go ahead and look at our data. So our data is our inputs. And we think of this as being a list of tuples where the first entry in this tuple is a dictionary, which essentially records the output of each of these, or answers to each of these questions of like, what level are they, a senior or mid-level or junior? What's their preferred language? What do they tweet or not? Do they have a PhD or not? And again, just sort of parsing through this, you can sort of see, all right, false, this candidate didn't interview well. And so they didn't have a PhD, didn't tweet, and they're looking for a senior level position. This one's also false, and this person did have a PhD, so maybe not tweeting is a big predictor. Here we go, mid-level, Python, tweets, no, and so on and so forth. So you can spend some time kind of reading through and maybe guessing how you think this classification rule is going to work. But again, purpose of this class is to sort of tell you about existing algorithms and see them in action. I'll warn you that this is completely fabricated data, so try not to take any of the conclusions seriously. All right, so just make sure I bring that into memory. All right, so now we finally get to the Id3 algorithm. So essentially what we're trying to do is use these notions of entropy and information gain, where we want to maximize the amount of information gain as we split into our different bags, which are then going to be split on further and further. And then ideally having a decision rule, which allows us to decide, all right, which side of the branch do you belong on? And this will give us essentially a hiring tree. The algorithm for doing this, and there are plenty of other ones, but this is called Id3. That's the iterative dichotomizer 3. So dichotomy, think of 2. So we're sort of splitting, and we're going to iterate this splitting procedure. So that's the basic idea. It's a tree algorithm. It's going to produce a tree, a decision tree as an output, and it's somewhat defined recursively or iteratively, as you'd guess from the name. So if the data all have the same label, meaning we've gotten to a point where all our data have the same label, then we just end with a leaf node. And that means that if you got to this part of our decision tree, you can just stop and predict whatever that class label was. On the other hand, if the list of attributes is empty, so meaning there are no more questions or things you can split on. So again, you think of this list of attributes in our cases as a dictionary of attributes, then we have no more data to learn on. So we're going to just go ahead and create a leaf node. And as I've sort of alluded to earlier, if you have a most populous one, you're going to do best if you just predict that most common label is the right one. Again, that's just sort of the best you can do to maximize your expected correctness or average correctness. So you can think of these first 2 bullet points as if the data all have the same label, or if the list of attributes is empty, as essentially base cases in this iterative or recursive algorithm. So we now get to let's look at these otherwise statements. So otherwise, what we're going to do is try partitioning the data by each of the attributes. So meaning, we can pick an attribute, let's say has a PhD, and then we can just look at all the possible values for that attribute. In this case, yes or no. It's a binary option. And then we could just see like, okay, if I take my bag of data and then I separate all the people who have PhDs and all the people who don't have PhDs, I can ask, what's the entropy of that partition and how much information have I gained when I've gone from the unordered data to this one where I've partitioned into the people who have PhDs and people who don't have PhDs. That's going to give me a number. How much information was gained in that process? Alternatively, I could look at what languages did they learn on? And look at that partition. Again, in that case, we actually have lots of different sort of branches coming off corresponding to each of these, the answer to that question of what's your favorite language. And then that's going to give us also like an information gain. And so what we want to do is we want to choose the partition with the lowest partition entropy, because that's going to maximize the information gain. And then once we've made that choice, we've gone through our list of attributes, we see which one gives us the largest information gain, i.e. which partition has the lowest partition entropy. We then add that decision node based on that chosen attribute. And so now we've split our data according to this partition rule. And now for each of the remaining sort of nodes in this partition, we have still a non-empty list of attributes to try to partition on. And we repeat this process. It's partition based on the thing that maximizes entropy amongst the people who are in that node. All right, so let's see this in action. All right, so again, we're going to do this thing where we've got partition by, and they've got our inputs. Our inputs, remember, was a list of tuples, where the first entry in the tuple was a dictionary. And then we're going to go ahead and also feed them the attributes to look at. And so I'll just remark that this particular example, I think, comes from Joel Gruss's data science, not in a nutshell, but it's the book which essentially tries to get you to implement each of these algorithms from scratch, data science from scratch. And so that is they take this sort of type-based approach where they focus on what's the type of the input and what's the type of the output. And so here they're saying that the output's going to be a dictionary, which then takes the attribute values as sort of keys, and then tells you what inputs to look at. All right, so we'll spend some time trying to digest this code later, but let's just go ahead and look at the results here. So what do we have here? We're going to look at partitions, and then we're going to do this partition by. And again, these are functions we already defined earlier. We have our inputs and our attributes. And then for each of those, we're going to look at the partition entropy associated to the sort of values in that partition. And so we then step through all the possible keys in our dictionary, which again, you think of these as the keys in the attribute dictionary: level, language, tweets, PhD. Remember, this was the junior, mid, or senior. This was Python or Java or what have you, or R, and so on and so forth. And so when we start with our unordered data and we look at all four of these attributes, and then we ask, what is the distribution, or what are the different entropies that we get when we partition based on that label, on that key? Well, what do we see here? So we see that level gives us a pretty low entropy. So meaning that when we choose to partition our data based on, is this person a junior or a mid-level or a senior level candidate, we actually have the cleanest separation of our data. And indeed, the highest, the one where we have the most disorder, is the case where we partition based on PhD. So what this is essentially telling you, again, you think of the class labels here as higher or not higher. So we're basically doing the entropy of that Bernoulli random variable across each of those sets in that partition. We have the greatest mixing of higher or not higher candidates when we just choose to look at PhD, which essentially suggests that PhD is not a good predictor for whether or not a candidate's going to interview well, which we're using as a proxy for hiring. Again, this is fabricated data, and perhaps Joel Gruss is trying to poke some fun, but people with PhDs, but let's continue with it in good faith. So the conclusion is that the level has the lowest entropy out of all these attributes. So if you follow the Id3 algorithm, that says that we should split first based on that attribute. So what we then do is, we take our root node, which has all of our unpartitioned data. We're going to create a leaf, or sorry, an edge leading to 3 new internal nodes, which correspond to the junior, mid, and senior level. So let's look at then what happened when we actually go back to our data, which I've summarized on this slide. So notice that if you go back and look at the data, apparently everyone who was a mid-level candidate interviewed well. So that actually ends up ending, that gives us a leaf node. Everyone in that node, if you just looked at everyone who was a mid-level candidate, they interviewed well. You can just predict all the people in this. If they just tell you that they're interviewing for a mid-level position, then based on our training data, it looks like they're going to interview well. And so we predict that. That's our rule for classification. If they have a mid-level candidate, then we stop. So that ends up becoming a leaf node. Senior candidates, though, we do have a mix of trues and falses. And so we're going to need to split them again. So what happens there? So senior inputs, again, we're going to use list comprehension there. So we look at our input and label for input and label. Again, remember it's a tuple in inputs. If input happens to equal, if the input level equals senior, so I mean this Boolean expression evaluates the true, then we're going to include that tuple. So this basically gives us a way of like searching through our data of inputs and then just extracting out the ones that are seniors. All right, and so now what we can do is, again, the Id3 algorithm says, among those senior candidates, we're going to now partition based on each of these 3 possible keys: language, tweets, or whether or not they have a PhD. And again, just to make sure nothing changed, again, having a PhD seemed to have the highest entropy, so meaning the greatest mix of trues and falses, interviews well or doesn't interview well. Language is next highest, 0.4, but actually if you tweet or not, this apparently provides the lowest entropy. So the Id3 algorithm says, now that we've already partitioned once based on level, now we revisit each of our nodes that aren't leaf nodes, and then we recurse on the other remaining attributes. We pick the attribute which has the lowest entropy, i.e. the greatest information gain, to then further subdivide that node. And in this case, that means we choose whether or not the candidate tweets. So if we have a senior level candidate, we then need to look at whether or not they tweet or not. So the senior level candidates, yes tweets always resulted in true. So no tweets then ended up resulting in false. So this sort of suggests that if you're a senior level candidate, you should make sure your online presence is up there. And so one of the things you want to do in that case is, have an active Twitter presence, and then people are like, all right, this person's hip. That means they're probably going to be able to follow the latest trends. They're influencers, what have you. Those people interview well. So now we do the same thing on their junior node. And so it turns out that now our decision tree says, all right, if mid automatically interviews well, if senior asks if they tweet, they do tweet, that's also going to interview well. And now we can ask, all right, what about the junior level? Apparently, if you go through the junior level, they end up finding the lowest entropy partition comes from looking at PhD. And again, I think Gruss is poking fun at PhDs here by saying that no PhD always interviews well. People with PhDs tend to interview poorly. So I think they're trying to discourage you from going to graduate school above the master's level. And this is all summarized in this tree here. So first we ask about the level, senior, mid, junior. Then for junior, PhD means, do not hire. Not a PhD, yes, hire. And then tweets, yes or no. So if you do tweet, then that looks well. So notice again, this is a classification level algorithm. it means it takes in data, takes in a sample, a test sample, and it, by following the rules in this tree based on the observed attributes, the features, and notice here the features are categorical variables, which is a really nice thing to think about because a lot of the algorithms for classification we've considered have been one sort of more geometric, look at distance, look for separating hyperplanes, so on and so forth. But this is sort of more logical, categorical, and it provides this sort of decision tree as the rules for classification, which always ends up in one of the class labels that we're looking at. All right, so, we also get into questions such as, what are some of the problems that can go wrong with the Id3 algorithm? And so, again, since decision trees really, really look hard at the training data, and that's how they make their rules, we can end up with situations where we basically overfit our data using a decision tree. So one of the things that ends up happening is they end up using all the attributes. So you end up having a really, really deep tree. So let's imagine that we did a thing where we basically split our data into two. Again, maybe we'll go over this code in greater detail in class, but if we did this sort of partition by two, this is a setting where if we try to look at each of our attributes again, we end up getting essentially a virtual tie between language and level. And now you can ask yourselves, well, what if instead of doing that initial split based on level, we look at the split by language? And so what does that give us then? So partition by 3, 679.39 tweets then ends up becoming one of our lower attributes. And so what we end up doing is we end up seeing that we get sort of different rules for classification. And so as alluded to, we looked at the question of level first, but then there's also, just going back here briefly. So level was good there, but then with this partition by 2, we could have done language. And then if we did in another one, tweets actually came out as the winner. So all this is to say, so that we essentially are going to look at if we sort of separate out our data or try to do something kind of like cross-validation, we're going to end up getting different rules or decision trees. So this kind of gets at the idea of, maybe the thing we want to do is try to use the decision rules from lots of different trees and see which ones are sort of most common across all of them. So this gets into, a method in machine learning, and even sometimes goes to sort of, I won't call it neural nets, but essentially this is another important algorithm which you should be aware of, called random forests. And so what we do in this case is basically build multiple decision trees, and then we essentially let them vote on how to classify inputs. So again, the details for that are beyond this course, unfortunately, but again, I'm trying to contextualize how some of these other machine learning algorithms fit in with the broader scheme of things. All right, so I've listed a couple more references here, and again, going to the sort of data science from scratch PDF. I guess that has been taken down. There was an older version, and now there's a second edition. But there are several other Medium articles published underneath the heading of towards data science, and then we've also got a nice sort of plot which we essentially followed some of the earlier parts of in our lecture today. All right, so Again, I appreciate everything, all the work that you all have done in this class so far and the attention you put forward. And I look forward to seeing you in class soon.